More, oh, yeah. You're thinking of a similar thing to this kind of deal? And that's why I hate that your book gives you that rule separately, because no. Well, no, but yes, but no. So it almost did, like right here, but it kind of got sucked up into the 12 because it was also multiplied by that 4. So it does, but that's because it comes down as part of the derivative of the inside piece. When we were given the e to the kx rule, I said way back when this is technically a chain rule, and we didn't even know what chain rule was yet. So technically, if you think about like the derivative of e to the 3x as a chain rule, not that e to the kx thing, you would have e to the 3x, and then you'd have to take the derivative of the 3x, which would get you that 3 that we had. So it shouldn't come down separately. It's part of the chain rule where it gets tacked into that derivative of the inside piece at the end. Does that make sense? Okay. So that comes from part of the derivative of the inside piece. So this inside function here is the 3x to the 4th. So when I take the derivative of x to the 4th, I bring the power down and subtract 1 from the power. So the 4 minus 1 gives where that cubed comes from. It comes from the derivative of x to the 4th. Whoops. I am really thirsty. Okay, cool. Chain rule reminder. We have an outside function and an inside function. Here, outside function is essentially 10 times e to the z, if you will. We're essentially have something that looks like this, where that z is the 3x to the 4th. So the derivative, the chain rule tells me that I have to take the derivative of that. So the derivative of 10 e to the z would be 10 e to the z. But then I have to take the derivative of that inside piece. So I have to take the derivative of that exponent, if you will. So my 10 e to the z, essentially, is right here, that I just circled kind of in blue. That's really thin, and you can't see that it's blue. So this last piece comes from the derivative of the inside that we have to do for the chain rule. So that's where this is coming from. And so we have to take the derivative of 3x to the 4th. So the 4 comes along, the 3 comes along for the ride. You bring the power down, subtract 1 from the power to get the 4x cubed. So it's not really that we're bringing the 3 down per se. It's that we need to take the derivative of the inside, and that 3x to the 4th is the inside function. Does that make sense? Hopefully. Maybe. A little bit. Hooray. Any more questions on that one? Yeah.
Even though it's a chain rule, can you do like the party rule and the first rule? Now, I someone got the same one you got, but different though. I did like the F and G, and also F multiply and G multiply.
What were your F and G?
Okay, like for T, for G I have E over 3x over 4.
Okay.
For second F, 0.
Okay, so you took 10 times e to the 3x to the 4th?
Right.
That's perfectly fine. You can totally do that. And all right. I gotta erase this because it's getting in my way. All right, next one. Natural log of 5x squared minus 7 times x squared plus 1. This is going to be a product rule where essentially with the product rule, you want to essentially, well, I've said essentially one too many times. I was about to say it again. So we've got an x here and an x here, and they're kind of in completely separate pieces of this function. So since you have two occurrences of the variable and these things are being multiplied together, that should tip you off to product rule. So if I like to do my little chart, dude, I have natural log of 5x squared minus 7 and x squared plus 1. Take the derivative of each piece. Here we have a chain rule for that first piece. Outside function is the natural log, so we would get 1 over the inside. Chain rule says to then take the derivative of the inside, so we need to take the derivative of 5x squared minus 7, so you get 10x minus 0. So I'm just not going to write the minus 0. Derivative of x squared plus 1 should give you 2x plus 0. Product rule in general tells you f prime g plus fg prime. So we've got, I'm going to write f prime as 10x over 5x squared minus 7. If you leave it separated, perfectly fine. So I would write 10 over 5x squared minus 7 times x squared plus 1 plus natural log of, oh no, I'm running out of space. Ah, it's okay. I just kind of went a little bit into the other one. It'll be all right. I would suggest just leaving it there. There's really not much you can do to, I dropped an x. That should be a 10x. Oopsies. There's really not much you can do to simplify that, so just leave it. Questions, concerns on that one? Wait a couple seconds. Just in case. Oh, I can get rid of it. Okay. The last one was a quotient rule. So if I do my little chart doodad again, numerator is always the f, denominator is always the g. Anastasia, yeah, there should be. I'm pretty sure it's up. I do probably need to talk about that at the end of class because depending on how far we get today, that's going to change some things. But anyway, so we've got e to the x and x plus 1 all to the 5th. So derivative of e to the x is e to the x. Yes, I can. And then the derivative of g is going to be a chain rule. We're essentially in a something to a power case. So we do the power rule first, bring the power down, subtract 1 from the power, but leave the inside alone. Times the derivative of the x plus 1, which is just 1 plus 0. I'm going to leave it here, but not write it in the final answer because, you know, anything times 1 is just itself. But just so that we remember that it existed because of a chain rule, I'll leave it there. Generic quotient rule says f prime g minus fg prime all over g squared. So I always forget to put my g squared in my little chart thing. So that would be x plus 1 to the 5th all squared. I would personally take the 2 seconds it takes to rewrite that as x to the 10th, x plus 1 to the 10th. So we've got f prime times g minus f times g prime all over g squared. You could simplify this one a little bit. I would say just leave it. If this were a chapter 4 question, I would probably simplify it a little bit. Since essentially all of those terms have an x plus 1 to the something in it, you could start canceling some of them out. Yeah. The thing inside the parentheses is not just an x. I know it's not much more than an x, but it's not just x, so it's a chain rule. Any questions on this? And then Rihanna, I'll scroll back and. I still see someone scribbling, so hold on for 5 seconds. And then let's go back here really quick. Leave that up for a couple more seconds, and then we'll go on to chapter 4 notes. While I'm leaving this up, I guess I can babble a little bit. So it was my hope and dream to get through all of chapter 4 by the exam. I don't think I'll achieve my dream. And it has never happened to me so much that I've had to screw up all of your homeworks so many times. It's never happened to me in life. But after today, you're welcome. I'll see where we're at, and it's probably going to end up being that I'm just going to have the homework open for way longer until like the week after the exam. So essentially, there's chapter 4 homework up right now. It runs through 4.1 through 4.4. We should get through 4.2, but 4.3 and 4.4, I'm not entirely sure. So possibly what would happen is we would have our exam on Thursday. We would cover 4.3 and 4.4 probably on that next Tuesday. So I would just extend the homework that's currently open to be open until like, I don't know, the freaking end of the month by the looks of it, I think. Pretty much, 27th. So that, no, wait. The 3rd of November. Oh, Lord. We moving on. Yeah, because your exams then, so then we wouldn't get to 4.3, 4.4 until then. So I wanted, essentially, that chapter 4 homework would be open for 5 million bajillion years. But I'll talk about that more once at the end of class, once we see how far we get. Does someone have their hand up?
Yeah, I was just going to ask them again.
So yeah, the exam's on the 22nd, not today, but next week. So we'll go through as much as we can today before our quiz, of course. And then we will use some of Tuesday to cover material, but I do want to try to take out an okay amount of class to allow you guys to ask some questions if you want. That review packet, like for exam 1, I'm almost done it. And especially I need to figure out how far we get today. But that should be up tomorrow on Blackboard for you guys to look over. So let's get to it then. Chapter 4. So the other day we started this just barely. So remember we were talking about maxes and mins. So we have this idea of these local maxes and local mins. And we kind of started talking about this first kind of example, which is less of an example and more of just a demonstration of what's to come in a second. So we had been looking at, and we found the local min, and we talked about that a little bit. We found that the min looks to be at approximately x equals 1. So the derivative at that point would be probably 0, because we would have a straight horizontal tangent line. And then if you look to the left of that min, the function's decreasing. So we use the relationship between the function and the derivative to say that the derivative would therefore have to be negative. And then to the right, we have an increasing piece, so the derivative must have been positive. So that was like a brief, super run through of where all that came from. So let's do the same type of idea for the maximum. So where's the max looking to be? Well, I guess I already drew the dot. So it looks to be approximately at 1. So it looks like we end up having a max at maybe -1. And again, I'm saying maybe because maybe I'm slightly off, who knows. What would the derivative be there? Well, the same type of idea is we end up getting this kind of horizontal tangent line. So the derivative, the slope of that tangent line would be 0. So we would probably have that the derivative at -1, if that's the right point, would be equal to 0. Well, what's happening to the left and to the right of that point? Well, if we look to the left of it, the original function is increasing. If the original function is increasing, the derivative is positive. That relationship is highly important. So we would essentially have that the derivative is positive to the left. And I'm now writing it in a different notation than I did above. I'm going to rewrite that so that it matches the one above it. So to the left, the derivative would be positive. And let me just do an f is increasing kind of reminder of why that's a thing that I could say. And then if I look to the right of that max, we're decreasing. So if the original function is decreasing, the derivative is negative. again, this example was more of a demonstrate what we're going to use. Notice how in each one of those, the derivative changed sign. If I look at the derivative on the left and then the derivative on the right, it's opposite. The sign is opposite. In one direction it's positive, in the other direction it's negative. And notice for the min, it went from negative to positive, whereas with the max, it went from positive to negative. And that's actually the idea we're going to use to be able to find these without actually looking at the graph. If we can figure out what the derivative's doing around these certain points, we can figure out if they're maxes or mins. So that's essentially what we're going to do. My voice got really hot there. So let's do that. Let me drink more water. Talking for 3 hours is not. Don't do it. All right, here we go. So, lots of definitions first. Lots of definitions first. For any function f, a point P where f prime of P equals 0, so the derivative at that point is 0, or f prime of P is undefined. And please feel free to ask me to slow down if you are someone who is taking these purely by hand. I'm going to try to be slower than usual. I understand that when we get to these pieces, it's going to be gross. So if the derivative is 0 or undefined, it is called a critical point of the function. Now, unfortunately, note that the actual coordinate point, Pf of P, is also called a critical point. Because mathematicians couldn't be bothered to think of two different words. We're lazy. Well, f of P is referred to as the critical value. 95% of the time, and probably even more than that, but I'm going to be kind of conservative here. 95% of the time when they say critical point, they just care about the x value. 100% of the time, if I say critical point, I just care about the x value. If I want the y value, I will be very specific that I want the y value. But 100% of the time for me, and I'm pretty sure like 95% of the time for Wiley, if they say critical point, they just care about the x value. I'll breathe. So we have a theorem, which is just something that's true. So if we have a function that's continuous on the real line, which essentially means 98% of the functions we deal with has a, I need to talk about undefined in a second. Anyway, if it's continuous on the real line, which essentially just means you can draw it very nicely without picking up your pencil. No, my brain's breaking. So if a function has a critical point, has a local maximum, or a local minimum, at P, then P is a critical point. Got ahead of myself. Of the function. That means if f has a local max or a min at x, then f prime of x equals 0. Now you could say to me, well, you just said that a critical point could also be undefined, which I need to talk about more in a second. The places where the derivative is undefined are going to be points of interest, but they are like never maxes or mins. They're kind of a different kind of point of interest. So you can pretty much guarantee that if it's a max or a min, the derivative must have actually been 0 there. Now the converse of this statement, the converse means, you have, if it's got a local max or min, then it's got a critical point. If we flip-flop those critical point to max or min, it's not true. That is, a function can have a critical point but not a max or a min there. Most of the critical points that come from the undefined piece are not maxes or mins. But what that does mean is that if we find all of the critical points, we find all of the options for maxes or mins. They might not all be maxes or mins, but if there is a max or a min, it must be one of those critical points. So that's kind of what we're going to use. We're going to find these critical points and then also have something that's going to tell us whether or not it's actually a max or a min. Up to this undefined piece again. A function can be undefined for a variety of different situations, most of which are kind of outside the scope of this class. So in terms of what we're going to care about, what you need to look at to talk about undefined, the only time we're going to care about whether a function is undefined is when a denominator is 0. So if you take the derivative and your derivative has a denominator, like with a quotient rule, then you have to make sure that that derivative is never 0. So you're going to take that derivative and set it equal to 0. We should probably get to the point where we'll see an example of that in a second. Otherwise, if you take the derivative and there's no denominator, you don't care about undefined. The large majority of things we will look at, you don't have to worry about undefined. And again, there's a lot of other things that can make functions undefined, but we're not going to talk about them. All right. I'm going to skip example 1 really quick. We're going to come back to it in just a second, because I realize that I say find the first derivative number line, but I haven't really said what that means. So let me take down a few more notice things. I think most people have caught up to this point. And I'll be scrolling back up to this in a second. I can leave in some of that when we do that example 1, but let me scroll down here really quick. We'll come back to that example in a hot. If you were the person that I sent note to 5 million years ago, this is blank, and I'm really sorry. If you printed them out from when I sent them to you 5 million years ago. Anyway, so process for finding local extrema. Extrema is just a word to say maxes and mins at the same time. So I don't have to say max and min, I can just say extrema. So what we're going to do is we're going to find the derivative. We're going to set that sucker, so the derivative, we're going to set the derivative equal to 0. And also determine if it's ever undefined. This is going to find us our very lovely critical points. Now from here onward in the process, you have 2 choices. We're going to talk about the one of them today. I don't know if we'll get to the other one today, but we'll talk about that some other time. Probably on Tuesday. But anyway, there's 2 choices. You can either use something called the first derivative test, which is highly suggested, or you can use something called the second derivative test. So I'll kind of talk about why the second derivative test isn't as good necessarily. It's essentially that the second derivative test can sometimes tell you nothing, and then you have to use the first derivative test anyway. So usually people just default to using the first derivative test. Pause for a second. So what is the first derivative test? So the first derivative test, also to reiterate, so no matter which way you go, you always do those first 2 steps, and then you get to pick. But anyway, so say we do the first derivative test. So we just found the derivative. We set it equal to 0. We found all our critical points. What we're going to do is we're going to create a number line, which is why I skipped that example, because I said find a number line and I didn't. And you don't know why you were going to do that. We're going to find a number line. We're going to plop the critical points on there. We're going to choose a test point from each section of the number line. So essentially, once we slap those numbers on there, we've kind of got it split up into these kind of sections. We're going to plug these into the derivative. You're going to plug them into the derivative. You're going to plug them in to the derivative. You're going to plug them into the derivative. You're going to plug them into the derivative. And now you're never going to forget because I said it about 5 times like an idiot. But people always plug it into the wrong spot. So you plug them into the derivative. And you need to find whether it's positive or negative. So in some cases, we'll probably see in the example in a second, you don't even necessarily need to figure out what the number is. Sometimes you can get kind of good at just realizing whether it's going to be a positive or a negative number. So if you can do that, go right ahead. You don't have to find the actual number. Or you can find the actual number. Is it positive, is it negative? Anyway, we'll see that in a second. You're going to then use that sign chart to determine if each critical point is either a local max, a local min, or neither. That's an option. Local max, local min, or neither. How the heck are we going to figure out which one it is? Here's how. Zoom in a little bit. Woo. So essentially, we're going to have these like number lines. And I always like to put an F prime next to them so I remember about the derivative, so I remember to plug them into the derivative. Okay, so we're going to have these number lines with some labels on them. Well, we're only going to have one, but I need to demonstrate 2 different things. And we're going to have whether the derivative was positive or negative. So say the derivative was negative to the left of P and of P. Another thing I personally like to do is I like to draw little line segments to tell me what the original function would be doing at those intervals. So if the derivative is, so Anastasia, so at an actual example, you would only have one number line, but I need to demonstrate 2 different ideas. So I'm kind of, think of these as 2 completely separate number lines for completely separate problems. Yes, they both have P on them, but that's just because I have to demonstrate 2 different situations. Where was I? So if the derivative is negative, the original function is decreasing. So why don't I draw the little decreasing thing? There. And then if the derivative is positive, then the original function would be increasing. I think drawing the little lines makes it very obvious that that's going to end up being a min. So we would have a local min at x equals p. If you were to be taking this class with me way back when I learned this 5 million bajillion years ago, it feels like, I would actually take exams and I would be like this. And my professors would look at me like I had 5 heads. And I was like, it's okay. I'm just figuring it. And yeah. Anyway, the other case is what if it changes from positive to negative, the derivative? Well, if the derivative is positive, the original function is increasing. If the derivative is negative, the original function is decreasing. So we would have a local max at x equals p. And again, you're not going to have multiple derivative number, well, you're not going to have multiple first derivative number lines for these problems. This is just, I needed to separate them into 2 cases. I could have put them all on one, but I feel like that would have made it more complicated. Anyway, and if it doesn't change sign at all, if it's positive, positive, or negative, negative, then it's neither. If it doesn't change sign, then it's the neither option. Savvy? Yeah. No. The first derivative test always is just conclusive. Like, you don't need to triple check anything else. That would just mean usually what ends up happening, and I can say this because I know you know what I'm talking about, that's usually something like it's probably going to end up being an inflection point. And it's just like, it just happened to also make the derivative equal to 0. But no, you never have to like double check the first derivative test. First derivative test always just gives you the straight answer. All right, so let's go back up and hit that example that I missed. So this one's kind of like a intro baby example, and then we'll do one full example, and that'll probably be as much as we can get to. So say I want to find the first derivative number line for x cubed. So that's kind of what I was talking about. We're going to find the critical points, put them on a number line, and figure out if the derivative is positive or negative. So first thing I need is the derivative. First thing I need is to click the draw button. I need the derivative. Derivative of x cubed is 3x squared. I need to set that derivative equal to 0, which means that I would have 0 equals 3x squared. Let me try unsharing and resharing and see if that helps the lag. Or makes the lag worse. So hopefully your algebra is up to snuff. If we divide both sides by 3 and then take the square root, we would get x equals 0. I don't have a lot of space to write all that, so hopefully y'all just follow that. That would mean that x is 0. So I don't have any denominators in that derivative, so I don't need to care about undefined. So this is going to be my only critical point. I don't have any more places where this function is 0. I don't have any denominators to check. That's my only critical point. So I'm going to go ahead and draw my number line. I'm going to label with f prime so I remember where to plug in all the values that I'm going to use. I'm going to tack the 0 on there. And now I need to choose test points. So notice how that essentially breaks that number line up into 2 parts. So I need a number that's greater than 0. I like to do these in other colors, or I like to write a little like I dash instead of just a regular dash, so I remember which are my critical points and which are the test points, because you'll need to remember which ones are which. Pick any number greater than 0. Let's just go with 1. It does not matter what number you pick, okay? It just might make the arithmetic more terrible. I need a number less than 0. Why not -1? Whatever floats your boat. Sometimes I like to be outrageous and I choose things like 100 and -100, because then I can just tell whether it's going to be positive or negative, because if it's something like x plus 7, well, 100 plus 7 is going to be positive, and -100 plus 7 is going to be negative. So sometimes going obnoxious can actually make it a little bit easier. But whatever floats your boat, you can always just plug it into a calculator. Anyway, so where do we plug those into? We plug them into the derivative. I'm having a blast today. I don't know about y'all. So we plug them into the derivative, so we'll have 3 times 1 squared and 3 times -1 squared, which in both cases is 3. 3 is a positive number, so that means that the test point of 1, this is a little high up. I should have drawn this down a little farther, just for my own sanity. Sorry. Now I made that number line really long now. Okay. 1, -1. So when I plugged in 1, I got a positive value. When I plugged in -1, I got a positive value. My function is therefore increasing and then increasing again. My derivative does not change sign. I do not have a max or a min there, so I don't have a max or a min at all. So no local extrema. So just because it's a critical point does not mean it's a max or a min. You have to check. Savvy? Okay, we have time to do one full example. Yes. And that'll be probably it. This technically is a full example, but it doesn't feel full because it's a simple equation. Anyway, I should stop using the word simple. We're skipping the second derivative test, and we're jumping down to example 3 if you're following my notes. If you're doing it by hand, it doesn't matter. Use whichever derivative test you like. Haha, we only know the first derivative test, so we're using that one to find the local max and min of this function. First thing, find the derivative. So let me kind of I'll write the steps kind of along the way so we remember what's going on. So we have to find the derivative. Oh boy, that is a quotient rule. So let me do my little chart boy up here. try to make sure I have enough space to do everything else I need to do. So if I find all my pieces for my quotient rule, derivative of x is 1. Derivative of x squared plus 1 is 2x. I know I'm going to need g squared, but just to save myself the tiniest bit of space, I'm just not going to write it in my little chart, dude. So we have f prime times g minus f times g prime all over g squared. Now, I think I hope I said, at some point in chapter 3 that, well, I don't care about simplification for those generic derivative questions. In this case, we're going to want to simplify. It's going to make our algebra life a lot easier for the next step. That denominator can just stay. So the main thing that I want to simplify is this numerator. So I'm going to come off to the side and just simplify the numerator and then rewrite the derivative. So that's why I'm kind of trying to remind us that I'm just pulling the numerator for a second to just simplify it. So I essentially have x squared plus 1 minus 2x squared. If I multiply that x and that 2x. So I'll end up with 1 minus x squared. So my derivative will be 1 minus x squared all over x squared plus 1 all squared. That is simplified enough that it'll help us out. If you didn't simplify, you could still do the rest of it. It's just that you would have to do the tiniest bit more algebra. Well, really, I guess you do the algebra no matter what, but anyway. For this one, for some of them, it'll help a bit better, but for this one, you either do the algebra and the simplification now or later. Anyway. So we found the derivative. Find critical points. Find crit points. Two options for a critical point. The derivative is 0 or the derivative is undefined. We have a denominator here, so we'll have to check that. So first, let's do the derivative equals 0. So 1 minus x squared all over x squared plus 1 all squared equals 0. I would take that entire denominator and multiply it over to the other side, but anything times 0 is 0, so that's super nice. I'm just left with 1 minus x squared equals 0. Or, shortcut, whenever you have a fraction, which is what that technically is, the only way a fraction is 0 is if the numerator is 0. So if you want to just take a shortcut and just write numerator equals 0 whenever you have a fraction and need to set the derivative equal to 0, you can do that. If you don't want to do that, or if that freaks you out, this way, because you just multiply both sides by the denominator and it goes away anyway. Add x squared over to both sides, take the square root. Remember way back from algebra that when you square root something, you pick up a plus minus. Because technically, -1 squared is +1. So you want to include that one as your option. I also need, oh, sorry, hold on a second. Since I have a denominator in this derivative, I need to make sure that it's not equal to 0. So essentially I need to consider undefined. So let me take that denominator and set it equal to 0. That's how you'll look and see where it's undefined, is you'll take that denominator, you'll set it equal to 0. If I square, you might be able to see what the answer is going to turn out to be, and if you can see it, you can kind of just say it. But if you don't see it, we would square root both sides. Plus minus 0 is just 0, so we don't need to consider two cases here. Subtract 1 from both sides is what I would do. You could subtract the x squared. Then you'd have to do an extra algebra step, but square root of -1. Well, technically in mathematics it exists. It's an imaginary number. In the course of this class, we don't do that. So we can't take the square root of a negative number, so this never happens. So essentially that just means that we don't have any more critical points from the undefined piece. Like we did need to check, but we just didn't get any more points. Number line time. These are kind of long questions. I will be quite honest. These get a little tedious. Any questions so far before I continue? Oh. Okay, so we've got a number line. I like to label it with F prime so I remember where I'm plugging things in. And the only critical points we had were at -1 and 1. Dang it, my magic isn't working. Anyway. Pick test points. So we have 3 kind of sections going on. So I have to pick 3 test points. I need something less than 1. I don't know, I'm going to pick -5 just for giggles. I need something between -1 and 1. I'm not crazy. I'm going to pick 0. Otherwise, I'd be picking a decimal, and I ain't doing that. Sometimes you're forced to pick decimals, but if you're not. And then something greater than 1. I like to be symmetric, so I'm going to pick 5 over here, too. Again, it does not matter what number you pick. Whatever number you want. As long as you did everything else right, it shouldn't matter. So we take those test points and we plug them into the derivative. To the derivative. I'm gonna make a song out of it. Sing it for you every day. Get sick of it. You want me to go away? No one can see this stupid idiot. I always forget that this is on my face. Anyway, here we go. So remember that our derivative was this 1 minus x squared over x squared plus 1 all squared. So my numerator, if I plug in -5, I'll get 1 minus, that's not 1. I'll get 1 minus 25 all over essentially 26 squared. So let me write 25 plus 1 all squared if I'm trying to be. So that'll be -24 over 6 squared. And this is what I mean by go. Okay, this is what I mean by I don't care what the number is. I don't know what 26 squared is. I don't want to type it in my calculator either, but I'm going to have a negative divided by a positive, which is going to be a negative number. So this is less than 0. I don't even know what the number is, but I know it's negative. So when I plugged in -5, I got a negative number. I put my work too close to my number line again. Gosh darn it. Anyway, eventually there will be a negative above that negative. There we go. Plug in 0, what do we get? We'll get 1 minus 0 over 1 squared. Well, hopefully that's easy enough to just calculate the number for. That's 1, which is a positive number. So we have a positive piece there. Plug in +5. We'll actually pretty much get the same thing as plugging in -5. We'll get, now I'm running out of space. Let me move that down a little bit. F prime of 5. So 1 minus 25 over 1 plus 25 all squared again. So we end up getting that -24 over 26 squared, whatever the heck that is. It's negative. We get a negative piece there. I wish I had put my work down a little farther so I could draw my little lines without running into all that. But essentially I have, you know, a decreasing, an increasing, and a decreasing piece. So sorry that my lines kind of overlapped there. I usually put them underneath, but I don't have the space there because I didn't think ahead. So again, I personally draw those little lines because then I can just kind of look at it and figure out which one it is. Technically, it's specifically because the derivative changes from negative to positive that -1 is going to be a min, and specifically because it changes from positive to negative, that's going to be a max. So we have a local min at x equals -1, a local max at x equals +1. Questions, concerns So yeah, Anastasia.
Sorry, would you go over again? How did you figure out that it's a local min at x equals -1 and a local max at x equals 1?
So let me redraw my chart over here so that I have more space. That's a large chart. Anyway, so essentially this is what I got from my chart. Negative, positive, negative. Now, if the derivative is negative, my original function is decreasing. So let me imagine like this little decreasing piece. And if my derivative is positive, then my original function is increasing. And then again, if my derivative is negative, my original function is decreasing. So these kind of lines kind of tell me what the function's kind of doing. So if the derivative changes from negative to positive, I end up kind of at a point down here. Oh, it's lagging. There we go. A point down there. So since we go from decreasing to increasing for the original function, I must have been at a minimum value. That's the only way that I can change from going down to going up, is if I was at like the lowest point in that kind of section. And then at x equals 1, I'm changing from positive, increasing, so positive derivative, so increasing function, to negative derivative, so decreasing function. So going from increasing to decreasing means that I must have been at kind of this highest point up here, so that must be a local max. Does that make sense?
Yeah, it does. Thank you so much.
You're welcome. So that's how we're going to do those. I have about 2 minutes before I usually give you the quiz, so I want to babble about something really quick. If there are any more questions, feel free to ask those too. So with what we have left to cover, we should be able to finish 4-2 on Tuesday. But I've never been this behind in a class in my life. So what that means is that what I'm going to do is, instead of trying to rush 4-3 and 4-4, because that's just stupid, what I'm going to do is I'm going to take so chapters 2 through 4 are all about derivatives. I like to have all of that on one test, because then we move on to integrals, which are a completely separate idea. So what I'm going to do is we're going to have our test. After the test, we're going to cover 4-3 and 4-4, which is still derivative stuff. What's going to happen is that material is not going to show up on your third exam, but it will show up on your final, so that the third exam can just focus on integrals. Okay, so that's kind of what I'm going to do. And like I said before, with that homework, it's just going to be essentially open for 5 million bajillion years. And we do that Tuesday after we take the exam. So we take the exam on the 22nd. We do 4-3, 4-4 on the 27th. So that chapter 4 homework, that's already up, and you should try 4-1, because that stuff will be on your exam. 4-1 and most likely 4-2 will be on your exam. But that homework for chapter 4 will not be due until November 3rd, which just sounds so far away, but it's not. And I'll keep reminding you of that as it shows up. But essentially, you don't have to do the whole entire chapter 4, because we haven't covered it all yet. So that's the thing. Anyway, let's take our quiz. Let me get y'all the recording and off of the big screen.